Hello and welcome to part 1 of our amazing lecture 11, where we will do the recap of lecture 10. So, what did we consider in lecture 10? Well, we considered the diagonalization of a Lagrangian. And how did we do that? Well, we went from the regular Lagrangian to its diagonalized form, which is 1/2 of Tij times eta dot eta j dot minus Vij times eta I times eta j. Great, simple enough, right? Well, then what we've done, we've wrote down what is the kth conjugate momentum through this, where there should be a q dot over here, of course, and as a result, we have been able to obtain the equations of motion. Tki times eta double dot I is equal to minus Vki times eta I. And then we were able to write it in the vector form. T times eta is equal to minus V times eta. Here we have plugged in an oscillatory solution for eta. And we were able to get at the eigenvalue problem. V times A is equal to lambda times T times A, where lambda is equal to omega squared. What we're looking for is for a coherent sinusoidal solution to the problem. And we came up with a bunch of different solutions for this. Each solution has its own eigenvalue or eigenfrequency, and it also has its own eigenvector, or kind of the direction of the oscillation. So we've gotten out of here a bunch of different eigenvectors and also a bunch of different eigenvalues. So what we've done, we've put together these eigenvectors into a matrix of eigenvectors that we called A, and we also have done the same thing with eigenvalues, but we have put them along the diagonal. So this is our eigenvalue matrix. We also put them into a single vector, lambda, which we denoted simply by lambda. So that is the notation. And now that we've defined this notation, here are the results. We found that A and lambda are both real, which means that we don't have to deal with complex numbers here. If we take a complex conjugate, we're gonna get back the same exact value. That simplifies life dramatically. And what we also found is that if we write down different vectors and take the product with each other, so if we do something like this, A tilde times T times A. So this is our special way of taking the dot product of different eigenvectors, but we're doing this for all of them at the same time because matrix combines all of them. What we found is that different eigenvectors are orthogonal to each other. So we have something non-zero on the diagonal, but outside of the diagonal, we have zeros. What is sitting along the diagonal? Well, it turns out it's a normalization of each vector. So it's the length of vector 1 squared, length of vector 2 squared, and length of vector n squared. For simplicity, at the end of last lecture, I decided not to worry about normalization, so I assumed all the eigenvectors are normalized, so all of these L's are 1s. How do you normalize an eigenvector? Well, if we found that the length of eigenvector is L1, we divide each of its components by L1, and then this L1 will become 1. And so we're going to get this. We're going to get an identity matrix after we've normalized the eigenvectors. So that is really useful, as we will see in the next part of this lecture. Finally, what we've also found is that the V matrix is actually also diagonalized by the matrix of eigenvectors, but along the diagonal we get the eigenvalues. So this looks almost like that, except now we do have non-unity values along the diagonal, and in fact we are getting this to be equal to our matrix of eigenvalues. So these are the most important results that we have obtained in the previous lecture. Thanks for the attention. Please don't forget to do the quiz, and we're going to have more fun in part 2 of this lecture. Stay tuned. See you. Hello and welcome to part 2 of lecture 11. And today, in this part, we are going to be talking about normal modes. What are normal modes? Well, we kind of had a mini discussion of this in the end of the previous part. If you randomly perturb a system from equilibrium, like now, we hear a thump, which means that our system will oscillate at a bunch of different eigenfrequencies. So if we randomly perturb a system from equilibrium, it will in general undergo not one vibration, but as we heard in the thump, multiple vibrations, in general n vibrations, each at different frequencies, omega 1, omega 2, omega 3, omega n, and these are the frequencies of free vibration, or resonant frequencies of the system. So let us try and separate the solution into these individual normal, as they called, modes. And for that, you will be surprised, but we will actually need the eigenvector matrix A, and we will also want it to be normalized. So why is it important for the eigenvector matrix to be normalized, and why do we need it at all? Well, remember that A times T times A is equal to an identity matrix if eigenvectors are normalized. So in this case, we're going to get a unitary matrix here. However, this also means that the inverse of A is going to be equal to, let us multiply both sides from the right-hand side by the inverse of A. We're going to get that inverse of A is equal to A tilde times T. So it turns out that if we normalized our eigenvectors, then the inverse of the eigenvector matrix A is very simply just the product of A tilde, the transpose of A, times the T matrix. Isn't that convenient? We don't have to worry about finding the inverse of a matrix, which is actually a rather computationally expensive problem, both by hand or on a computer. So this means that if we have an eigenvalue matrix that's normalized, it's very easy to invert it. So let us now start with a general solution, and let's see how to pull it apart into individual components. So our general solution can be written out as follows. Eta is equal to the sum over all of the eigenmodes of the real parts, because of course what oscillates is the real part, not the imaginary part, of our eigenmodes taken with coefficients. So eigenmode k is going to be taken with a weight or coefficient ck, and of course we want to include the time dependence e to the minus I omega k times t. So we have this really nice weighted sum of our eigenmodes. Okay, that's pretty convenient. Good. So let us now try and write down the solution to our system as it evolves in time, starting with some sort of initial condition eta 0. So suppose that we are given eta of 0 and eta dot of 0. So these are initial conditions. So for these initial conditions, we should in principle be able to evolve the system forever in time. For all time, we will know this because we're given the initial position, initial velocity. That should be sufficient to integrate our Euler-Lagrange equations in time. So let us try and figure out what is the right set of weights that will give us the right solution, because set of weights determines the solution exactly for all time. So from here, what we're trying to find is what is ck in order to satisfy this. Well, let us write down what our solution would be at the initial time, and that would be eta of 0 is going to be equal to the sum over k of the real part of ck times ak, and all of these exponents are going to be just ones, right? Because if we plug in 0 for t, e to the minus power of 0 is 1. So that's nice. What about eta dot? Eta dot of 0 is going to be equal to the same sum over k, but here we're going to take the time derivative of this. So we're going to get minus I omega k on the front. So that's precisely what we're going to get. And we're going to close the parentheses. Because again, once we've taken the time derivative, we'll plug in 0 for t, we're going to get E1 for the prefactor. Okay, that is pretty good. So see, we have a real part of minus I. So what can we do about that? So the real part of minus I times something is actually going to be a sum of the imaginary parts that correspond to that. Imaginary part of ck. Because if ck, let's say, is I, if we were to multiply by minus I, we were going to get 1. So that's precisely why the imaginary part of ck is what we're going to get out of here. So that is good. And then what we can do is we can write down what is the ith component of all of that. So let me try and take the ith component of all of this and the ith component of all of that, and we are going to write it down in blue so that we don't confuse vector notation with per component notation. This is going to be the sum over k of aik times omega k times the imaginary part of ck. And here we can continue this equality all the way to here. This is going to be equal to the sum over k of a I k times the real parts of ck. So you can see that the coordinate itself and the derivative of the coordinate itself, they look very similar. It's just one of them is determined by the real parts of these magnitudes, or the prefactors, and the other one is determined by the imaginary parts. So let us try and invert this equation. Let's solve for ck. The way we can do that is in the matrix notation, we can multiply by the inverse of this matrix. And we can say that the real part of C vector, and we're going to take its kth component, is going to be equal to the real part of ck, and that is going to be the inverse of matrix A multiplied by the initial condition vector, kth component, and that will be by this, the transpose of A times the T matrix times the vector of the initial coordinates. Let us now do exactly the same thing for the velocities. Let us now solve for omega k times imaginary part of ck. So that will be omega times imaginary part of c all k, where omega is going to be equal to omega 1, omega 2, omega n along the diagonal, very similar to the lambda matrix. So that will be equal to simply omega k times imaginary part of ck, and that will be from here in the matrix notation equal to the inverse A. We're going to take it over to here, and we will multiply it by eta dot of 0. Take the kth component, because it's kth component, and using the same exact trick of replacing a to the minus first power with a tilde times t, we're going to get that this is a tilde times t times eta dot 0 all of it is the kth component. So what is the sort of solution that we're going to get for our favorite C? Well, we see that we have the kth component of it here, and so we can write out that ck is going to be equal to the real component of it, which is just that, a tilde times t times eta 0 k plus ai over omega k times a tilde times t times eta dot of 0, and that will be k as well. So that is as simple as it gets. But we can actually move from here completely to the vector notation by making use of this matrix. And we can write that C as a vector is equal to a tilde, a vector, times t, sorry, a tilde matrix times t times eta times eta of 0, a vector, plus I, the imaginary number, inverse of the omega matrix, this one, that is omega, and times nothing but this, a tilde times t times eta dot of 0. So this is going to be our awesome solution for the coefficients that determine the evolution of our linearized system into the future. And as you can see, we didn't have to invert any matrices. I mean, inverting omega matrix is trivial. You basically replace omega 1, omega 2, and so on, omega n along the diagonal with the inverse values. So this actually is a trivial inverse. But what we've been able to avoid is inverting matrix A itself. And this is precisely why normalizing the eigenvectors is such a great idea. So let us see how we can make use of this, a solution for the evolution of the system in time, in order to pull our system apart into the normal modes. Please do the quiz, and we're going to get to those modes. See you. Hello and welcome to part 3 of our awesome lecture 11. And here we finally have gotten to the amazing part of normal coordinates. So what's normal about them? Well, normal is because they behave like a normal, ordinary harmonic oscillator. Just a sine wave for each of the coordinates. So these are really the fundamental building blocks of complex systems. What we've done, we've diagonalized the complex interacting system and broke it down into these constituents building blocks. And the way we're doing this is rather simple. We're just saying that our deviation from equilibrium vector eta is the sum of ak times psi k, where psi is our normal coordinate. It's just some amplitude times the sinusoidal variation. It's just a sine, e to the minus I times omega kt. So in matrix form, what we're going to get is that eta is equal to a times psi. And therefore, from here, psi is going to be a to the minus first power, the inverse of a, times eta. Or by this expression, it will be a tilde times t times eta. And if we take our equations of motion, which are t times eta double dot is equal to minus v times eta, and we plug in this expression into here, then we are going to get, let's see what we're going to get. So a times psi comes over here, and we're going to get t times a times psi double dot is going to be equal to minus v times a times psi. And see, something starts to make sense. What if we multiply this from the left by a tilde? And see now, once we've done that, this is just an identity matrix, and this is just a lambda matrix, which is equal to omega squared matrix. So from here, we can immediately say that our equations of motion become psi k double dot is equal to minus omega k squared times psi k. So our complex system with multiple eigenmodes can actually be linearized in these normal coordinates, where each of the coordinates oscillates just like an independent oscillator. So let's try and get an idea of whether this indeed is true if we were to write down the Lagrangian in this form, because if indeed we've linearized the system and broken it down into a system of independent oscillators without any couplings between them, then our Lagrangian should drop out into individual contributions from each of these oscillators. Let's see if this indeed holds true. So our Lagrangian is t minus v, and it's going to be given by 1/2 of eta dot times t times eta minus 1/2 of eta tilde times v times eta. Just one underline. Times v times eta. And this is where we're going to plug in exactly the same expression. It's going to go in here, and in there. So what does it look like? If we plug in this here and do the transpose, then psi is going to come up on the front. So it's going to be psi transpose dot. And then here we're going to get A transpose times T. And then from here we're going to get A. And then we're going to get psi dot over here as well. And then we're going to subtract off from here 1/2. We're going to get eta transpose. So it means we're going to get psi transpose, A transpose, V times another A from this, from this, times psi. And you can see an unmistakable emergence of exactly the same sort of things. This is I, and that is lambda. And so our Lagrangian simply becomes the sum of 1/2 of sigma, sorry, of psi dot square k minus 1/2 sum over k of lambda, which is omega k squared, times psi k squared. So indeed, our Lagrangian is simply the sum of the individual kinetic energies of the oscillators minus the sum of the individual potential energies of each of the individual oscillators. And from here, we of course can write down the equations of motion for each of these oscillators just like that. Psi k double dot is equal to minus omega k squared times psi k. So what we've done is we've diagonalized Lagrangian. And in kind of visual form, we've gone from something that looked like a complex interacting system of multiple or many interacting oscillators we've gone from this complicated system to something that is the sum of independent, not coupled oscillators. So from complex system to a bunch of linear oscillators. Amazing! We have simplified our lives dramatically. This is much more complicated than that. And this is the power of normal coordinates that allow us to diagonalize the Lagrangian and make our lives just a little bit simpler. Isn't that great? I will always take that. Thank you very much for your attention. Please do the quiz. See you. Bye-bye. Hi, hello, and welcome to lecture 11.4. Here we're going to make use of the machinery that we've developed in order to solve a problem. So let's take a look at a simplish system where we have a horizontal table. It's supposed to be horizontal. I'm sure that there is waviness over here. In this example, we have two masses which are attached to each other by a spring with a constant k. This mass is m1, that one is m2. And our goal is to find the eigenvalues and eigenvectors. So, first things first, what are going to be our generalized coordinates? And how many degrees of freedom do we have here? Well, we have two different masses, and therefore there will be two different coordinates that we need to specify in order to constrain the system. Therefore, the number of degrees of freedom is equal to 2, and our q1 will be equal to x1, and q2 will be equal to x2. All right, so one of them will be x1, and the other one will be x2. So if this is x, then this will be x1, and that will be x2. So these are the coordinates of the weights. And then we can easily write down what the kinetic energy is. It is m1 over 2 times x1 dot squared plus m2 over 2 times x2 dot squared. Our potential energy is going to be k over 2 times the distance between the two masses. So it will be x2 minus x1 squared. And from here, we can construct the T and the V matrices. So what is going to be our T matrix? Here we're going to put d2t dx1 dot squared. So it will be m1. Here and there it would be mixed derivatives, but because we don't have x1 dot times x2 dot term, those will be 0. And this one will be d2t dx2 dot squared, so this will be m2. What about v? Well, with v, it's very similar to t, except we take partial derivatives with respect to x1 and x2. So second partial derivative with respect to x1 is going to give us k over here. Same thing for x2, and we now do have the mixed derivatives here because we will also have the term here as a result of the square. If we expand it, we're going to get minus 2x1 x2. So for these off-diagonal terms, we're going to get minus k and minus k as well. So this is our T and this is our V matrix. So what is our eigenproblem? Well, as before, the determinant of minus omega squared T plus V is supposed to be equal to 0, and we can write it out. It will be the determinant of, let's take a look at that. So it will be the matrix. I will denote determinant with the vertical bars. So it will be minus omega squared times m1, right, plus v plus k. Here it will be minus omega squared times 0 plus k, so it will be minus k over here. Also, I missed the minus sign here, right? Here, by symmetry, it will be minus k, and then on the bottom right, it will be minus omega squared times m2, and we will add plus k. So that is our determinant, the one that is supposed to be equal to 0. Awesome. So let's expand what this determinant is. We will multiply this by that and subtract the product of these two, right? So it will be omega to the 4th times m1, m2. Then there will be minus omega squared times m1, m2 with a plus, and that will be multiplied by k, right? And there will also be a term plus k squared and minus k squared. So these two cancel. So now we have a quadratic equation for omega squared, where we have two roots. One is obviously omega is equal to 0, and the second one is given by omega squared, so this is gone. One of the omega squareds we can remove, so we're going to get this. It will be k times m1 plus m2 divided by m1 times m2. And this is the inverse of the reduced mass, so it will be k over mu, where mu is m1, m2 divided by m1 plus m2. So how do we compute the eigenvectors for this problem? Well, the equation for eigenvectors is this matrix multiplied by a1, a2. So if we look at the second line, it will be minus k times a1 plus minus omega squared m2 plus k times a2. So if we take a1 to be equal to this and a2 to be equal to minus that, we're going to get this a solution for a1, a2. So let's do precisely that. So we're going to take for a1, we're going to take just that, minus omega squared m2 plus k. And then for a2, we're going to get minus this, k. So let's check this. Plug this into here. I'll plug that into there, yeah, we're going to get them to cancel out. So the two possibilities for this is omega equal to 0, and if so, we're going to get the eigenvector to be proportional to 1, 1, right? Because this goes away, it will be kk or 1, 1. And the other possibility is omega is not equal to 0. So minus omega squared, it will be this, right? So it will be minus k times m1 plus m2 times m2 divided by m1, m2, right? Good. Multiplied by m2 plus k m1, m2 divided by m1, m2. And for the other one, we just have k. So that's pretty easy. All right, so what do we get here? Well, we immediately see that m1, m2 will cancel out. Right, so this term and that term, they cancel out. And as a result, we're going to get a really nice eigenvector, which will be minus k m1 over m2. And here it will be just k. So then we can cancel k, and we're going to get in the end that the eigenvector is proportional to minus m2 m1. So awesome, we have obtained the eigenvalues and eigenvectors. Now let us try and normalize our eigenvectors, which we will do in the next part. Stay tuned, don't forget to do the quiz, and I'm going to see you. Hello, and welcome back to the last part of lecture 11, 11.5. Now we're going to be normalizing the eigenvector. So right here, you see that we've obtained both eigenvectors for omega equal to 0 and the non-zero omega. And now our goal is to try and figure out how to normalize them. So let us construct a matrix made up of eigenvectors. The first one is going to be the 1, 1 eigenvector, which we denote as C1, C1, which will be the magnitude of our, or normalization of our eigenvector. And the second one will be minus C2 times M2, and it will be C2 times M1. Remember, the second one we found was proportional to minus M2, M1, and so C2 is the normalization of this eigenvector. The transpose of matrix A is going to be C1, C1, minus C2, M2, and C2, M1. So let us now compute what is A tilde times T times A. So let's do A tilde, let's leave A tilde out, and let us multiply it by T. Remember, T is right here. It's M1, 0, 0, M2. And we need to multiply it by A, which is right here. C1 minus C2, M2, C1, C2, M1, right? So what will this be? Well, it will be A tilde times the result of the product. And the result of the product, well, it will be M1, C1. For that one, it will be, let's see, right, M1, C1, then will be minus C2, M1, M2, minus C2, M1, M2, right? So what about this one? So it will be this times that, right? It will be M2 2c1, and will be this times that for this one, so it will be c2 m1 m2. And then we're going to take a tilde and plug it in over here. So now we need to multiply this by that, so we will plug this in here, and then let's write it over there. So when we multiply this, you will see that a lot of terms combine, and what we're going to get is m1 plus m2 times c1 squared, 0 over here, 0 over here, and c2 squared times m1 plus m2 times m1 m2 over here. And in order for our eigenvectors to be normalized, all of that needs to be equal to 1, 1, 0, 0. Remember, it has to be an identity matrix. So for normalization, demand. All right, so we demand this. So it means that this is equal to 1 and that is equal to 1 as well. So it means that our C1 is going to be equal to 1 over square root of m1 plus m2, and C2 is going to be equal to 1 divided by square root of m1 plus m2 times m1 m2. So that means that the normalized A from here will be equal to, so we're going to plug in C1 over there. So it will be, and we're going to plug in C2 over there, so we can take out 1 over square root of m1 m2. So let's try and figure out what this will be. So C1 will have 1 over square root of m1 plus m2. C2 will have that. So what we can do, we can take out as a factor 1 over square root of m1 plus m2. So then these two will be 1, 1, right? And over here we will have 1 over square root of m1, 2. M square root of m2 goes away, so it will be minus square root of m2 over m1. And here at the bottom it will be the inverse. So this is our matrix of eigenvectors which are normalized. And in order to compute this, well, we actually don't even need to multiply that because we know what the answer is. We're going to have omega squared over here and omega squared over there. So we're going to have zeros. Omega squared for the first eigenvector is 0, and omega squared for the second eigenvector is k over mu. Thank you very much for your attention. Please don't forget to do the quiz, and I'm going to see you in lecture 11, no, in lecture 12, where we will start working on frame transformations. See you there. Bye-bye.